This video will attempt to answer the question, why do sunspots appear to be dark? Perhaps you've seen a photograph of the photosphere of the sun, the region that emits visible light to us. And if it's during a time when there are dark patches on the photosphere, the sunspots, you can immediately see them because they appear to be darker. Why do they appear to be darker? So let's do some calculations here. Assuming that the regions are black bodies, that they emit power, joules per second, and calculated with the Blackbody equation, Stephan's constant times the area times temperature to the fourth power. So Stephan's constant is given in watts per square meter per Kelvin to the fourth power. And we're going to assume 1 meter squared of material in both regions at the higher temperature and at the lower temperature. So the general high temperature region would be called the photosphere, where the visible light is coming from. It's not the highest temperature on the sun by any means, by far. But let's calculate what we get for power for 1 square meter. So we start with Stephan's constant, 5.67 10 to the minus 8 watts per meter squared, Kelvin to the fourth for the units. We're doing this for 1 square meter, so that'll take care of the meter squared units. And then temperature to the fourth power, I have to use 5772 to the fourth power. So you ought to pause and do that calculation on your own. What I came up with was 6.293 times 10 to the 7th watts would be the power output from 1 square meter. That's a big number, 62 megawatts for 1 square meter. I'm a little bit surprised, but hopefully I haven't made an error in doing that calculation. So you certainly ought to check that. All right, that was the case of the photosphere. Now let's do inside the sunspot, where the source is solarscience.msfc.nasa.gov, and indicating a temperature of 3,700 Kelvin. And there's a range of temperatures that have been reported inside sunspots, and there is a range of temperatures, but let's say it's 3,700 Kelvin. So it's the same calculation, Stephan's constant. We use the same number because it is a constant. Again, 1 meter squared, but now I do 3,700 and take that to the fourth power. So again, you ought to pause and do this calculation on your own. I'm getting a value here of 1.063, if I can read my writing on my adjacent page, times 10 to the 7th watts. So we see here that there is more power being sent out into space from the photosphere material than from the sunspot material. And it's in the ratio of about 6. There's about 6 times the power being generated by 1 meter squared. Does that seem like that's the total explanation as to why sunspots are dark? The answer is no. Can you think of another reason that to our eye the sunspot might appear dark? Well, I'm going to sketch down here and then move it into your view. If I plot wavelength here and I plot the power or the energy emitted at a certain wavelength, and if I kind of freehand this would be a black body. Let's say this is the case of the 5772 Kelvin temperature in this curve. And right in here, it's around 500 nanometers, greenish yellow being over here. And our eye is built, green with 2 E's, our eye is built to make use of this light from the sun, where the sun is giving us extra energy compared to bluer wavelengths or redder wavelengths. And I can calculate, let's go ahead and do that. Again, the Blackbody formula gives us a means of calculating this peak wavelength. And this is, I'll just put P down here for peak. But the peak wavelength is 2.9 times 10 to the minus 3 meters times kelvins divided by temperature in Kelvin, no power. on the T. So this lambda is going to be 2.9 times 10 to the minus 3 meters times Kelvin divided by 5772 Kelvin. And that number, you find it on my page here, is 5.02 times 10 to the minus 7, or 502 times 10 to the minus 9, or 502 nanometers. That's our peak of where most of the energy, where the highest amount of energy is being emitted from the photosphere. What about the sunspot? Its peak is related to its temperature in the same way, 2.9 times 10 to the minus 3. I'm not going to worry about the units, and 3700. And for this one, if you divide those two numbers, you come up with 7.84 times 10 to the minus 7. I'll go right to nanometers, 784 nanometers. So the sunspot has its peak energy output, or power output, either way, at 784 nanometers. The photosphere material at 502 nanometers. So here's the 502 nanometers. It's true about black bodies. When they're cooler, they emit less energy at every wavelength. So if I was to draw the black body curve of power versus wavelength for the black body at 3700 Kelvin, I'm just going to guess at this. It looks something like this. I'm certain that it is underneath the photosphere curve at every place. That's a rule of black bodies. Sorry about that. It's a rule of black bodies that when the temperature is cooler, the power emitted at each wavelength is less than the power emitted by the higher temperature black body. And I haven't got a scale on here, but let's say this is 784 nanometers. So this is actually beyond the red. It's beyond the red. What colors of light does your eye see? Well, Roy G. Biv, red, orange, yellow, green for G, blue, indigo, violet for Biv. Your eye really is not very sensitive out here. This is into the near infrared. It's slightly past red, where the eye is sensitive to. So for two reasons, sunspots appear dark. There is less power, there's less energy per second being emitted by a factor of about 6. But I think probably even more important is that the sunlight is visible to your eye from the photosphere. The light from the sunspot is in a region that's not very visible to the eye, where the peak is. And when we're getting back into here to the reds, the power is even less. It's smaller than a factor of 6 compared to the power coming from the photosphere region. So I've not looked that up, but that's my interpretation. Sunspots look dark because there's less power being emitted, and also we have the bulk of the sunspot energy coming out in a wavelength that our eye cannot detect. So sunspots do look dark to us in contrast with the photosphere. If we would take this material out, this is much hotter than a blacksmith's fire, what have you, an iron furnace, where an iron production facility where they're melting iron. This is much higher than that, and you've perhaps seen videos where that material glows. If this sunspot material was sitting out in space, it would be very bright. But in contrast to the photosphere, it appears dark to our eye. So if you have questions about that, please ask your instructor.